Well, good morning. My name is Nathaniel Osgood. Today we're going to be talking about a fairly new topic within the health modeling landscape. That is the use of Bayesian Markov chain Monte Carlo techniques to help us derive posterior distribution estimates for the parameters of dynamic simulation models. That is, models that simulate systems over time. Now, the context of this work lies in limitations associated with a key component of the dynamic modeling process, namely parameter estimation through the use of calibration. Now, use of these terms varies over different sub-communities of the health modeling landscape, and broadly, I'm referring here to estimation of model parameters by comparison of the emergent behavior of our simulation models on the one hand with corresponding behavior observed from the external world. So, for example, we may be seeking to estimate the values of parameters concerning contact rate on which we have limited data directly from studies or from surveys that have been conducted through the use of the calibration process. Within this process, we observe how the simulation model as a whole behaves, or large subpieces of simulation model, in terms of its emergent behavior. It's behavior we wouldn't be able to just anticipate ahead of time. And we compare that emergent behavior against empirical data on corresponding quantities that we may have recourse to, and try to find values of model parameters that yield model behavior most closely corresponding to the empirical data that we have at hand. Traditionally, this process, which is a key one for estimating model parameters that we otherwise little know, this process traditionally gives us point estimates for parameter values. It gives us a set of values, one for each of the less well-known parameters, whereby the model best matches the empirical data that we have at hand. Now, in some cases, the approaches we may use may seek to give additionally confidence intervals via bootstrapping or other techniques. We may arrive at confidence intervals that express a degree of uncertainty concerning the values of these calibrated model parameters. Well, a very, very important and powerful component of the modeling, this traditional form of calibration does exhibit some very important limitations. One of the limitations that's most fundamental is that we are performing the calibration on a single dynamic model. That is, we are assuming, for the point of view of deriving model parameters, that we know the model structure exactly, and we're trying to identify the values of the parameters such that, conditional on that assumed model structure, the model behavior best matches our empirical data. This is a strong assumption. Often we're not exactly sure about the underlying structure. Perhaps there are several competing hypotheses as to what it involves. And yet, for the purposes of calibration, there's an important set of strictures that limit us to calibrating one model at a time. Second is that in many, many cases, we're emerging with just a single point estimate for parameter values. An estimate that doesn't really capture the degree of uncertainty associated with that, doesn't capture systematic variation in the uncertainty associated with, say, one parameter versus another. The fact that, for example, this model may closely match the empirical data, either if A and B are both high together, or A and B are both low together, but not other combinations. Or, for example, the fact that it can only match it closely if A is high and B is low, or vice versa. These sort of systematic variations in the uncertainty are not really captured within single point estimates. And these uncertainties may have important bearing on the outcomes of interventions. Even when we do have estimates of intervals within the underlying system, there's often a quite strong assumption that we're dealing with a unimodal system. These are local estimates, traditionally around this maximum likelihood estimate, for example, a single point estimate. And there's limited or no understanding of the global shape of the likelihood. We're not going to capture the fact, for example, that there's another peak nearly as high somewhere else within parameter space, within some other combination of parameters become nearly as good, and that may have quite significant implications for interventions, for example, we may seek to design. It turns out that associated with classic methods of optimization are often less well articulated or less explicit assumptions. Sometimes they lie completely implicit. For example, we may make assumptions about the distribution associated with errors through the metric by which we compare on the one hand model results and on the other the empirical data. And our imposition of these assumed distributions for errors may come with it significant challenges for particular practical problems where those distributions are not appropriate. We'd like some way to, for example, impose a more general criteria, one that would allow us to choose the different distributional assumptions in a more flexible fashion. Now, within this context, today, we're going to be introducing a very different approach. We're going to be trying to arrive not at point estimates, not at point estimates in confidence intervals that are centered around that point estimate point and measure only local features associated with likelihood. We're instead going to be dealing with an approach that helps us understand the relative likelihood of parameters, combinations drawn from across the parameter space that provide better understanding, as it were, to the broad distribution associated with parameter values across that space. Now, within this context, we're going to be dealing with some classic Bayesian concepts, ones associated with the distinguishing features of Bayesian approaches. That is the use of imposing a prior distribution, often before calibration, and arriving at a posterior. Let me give some notions at an intuitive level of those terms. Before calibration, we often have some sense as to where parameter values fall, or indeed some best guesses, not only to where parameters fall on the one hand, but also to which of several possible competing model structures may be most appropriate. Now, this best guess that we bring to the table prior to actually trying to match the empirical data we have at hand can be captured within a Bayesian approach using what's called a prior distribution. And it's called a prior because we can formulate it prior to observing the empirical data or settling on a particular model. So we're often going to be, we start with the option of imposing either weaker or stronger initial guesses as to the relative likelihood of different parameter values. And following this process, following the use of these Bayesian Markov chain Monte Carlo techniques, we arrive at an updated distribution which takes into account the empirical data and the relative likelihood as judged through simulation that particular model parameters can yield results compatible with or consistent with the empirical data. this resulting distribution that considers all those things, considers the sort of the plausibility, as it were, of different parameters by actually running the model and observing the consistency with the empirical data. We'll call this distribution the posterior distribution. So this distribution takes into account not only our best guesses for parameter values ahead of time, but also the likelihood through running the model that that model output, assuming those parameter values, could explain the observed data. Now, these posterior distributions, which are going to emerge from this process, are quite different and quite distinctive from the sort of point estimates that often come out of calibration. A posterior distribution over our parameters, and I'll denote here our parameters theta, bearing in mind that this may include not only parameters of the simulation model, but also parameters of a probabilistic model that I'll mention. So if we have some parameters and we arrive at a posterior distribution through this process we're going to be talking about using Markov chain Monte Carlo techniques, we can use that distribution to help us understand the relative likelihood of different particular parameter values in light of the observed data, one or more models that are under consideration, and what we brought to our prior, namely a pre-existing expectation beforehand of the relative likelihood of different parameter values. And typically, the insights from the observed data and its consistency with model results will overwhelm this sort of initial guesses. It makes our prior recedes the background in terms of the shape of the posterior. What dominates the posterior is often the consistency seen when we run the model between particular sets of parameter values and the observed data. Now, given such a posterior, there's all sorts of useful things we can do with it. For example, we can derive point estimates. For example, the maximum likelihood estimate. We could arrive at a mean estimate. Maximum likelihood estimate would be if we're assuming a sort of uninformative prior. We could arrive at a maximum a posteriori estimate. So the value, the highest density point within parameter space where the likelihood of posterior is the highest. We could arrive at a mean, for example, a minimum variance value, minimum variance estimate, etc. for parameters. But not only can we do that for parameters, we can do that as well for model output. That is, we can arrive at distributions associated with output from the model or models. We could, for example, arrive at distributions for what sort of behavior we expect going forward from now. And it will be a distribution, potentially a multimodal distribution, for example. So the posterior can give us these point estimates, as traditional calibration techniques do, but provides us a great choice of flexibility as to choosing what point estimate we wish to elicit. We can also arrive at these distributions over model outputs. We can arrive at distributions over for example, the relative distributions over how much better intervention A is than intervention B with respect to some particular metric. For instance, quality adjusted life years lived. Or we can ask what's the likelihood, for example, that intervention A is better than intervention B in terms of various outcome measures. This posterior over the parameters can also be used to arrive at credibility intervals for diverse model output, which have a certain conceptual underlying relationship with confidence intervals, but are formulated in a Bayesian form. So Markov chain Monte Carlo techniques helps us to reliably derive posterior distributions for parameters. Now, what's really notable here is that it's a very principled and general way for arriving at these approximations to these distributions. we have a very regularized way of generating samples, in particular, from this the distribution, and we can use that to derive these to arrive at these derived distributions for outputs, for example. So it will provide us a way, fundamentally, of sampling from the posterior distribution, or an approximation there too. And we can sample again and again and again, and hence we call it a Monte Carlo technique. So that second MC and MCMC, Markov chain Monte Carlo. We'll be arriving at just getting a glimpse of where that Markov chain lies implicitly behind this. So the idea is that using these techniques, they're going to provide us a way of specifying or arriving at the posterior distribution, not by giving us a functional form of it generally, because with simulation models we generally don't have the option of arriving at an analytic form for the posterior distribution, as you might with conjugate distributions and some traditional analytic MCMC approaches. Instead, we're going to numerically sample from this distribution, where the distribution itself will not be ever explicitly represented. Instead, we're just going to be able to sample from it. For each sample, for example, we could accumulate various statistics, running sample means, record likelihood at the point, etc., record the shape of the distribution. But broadly speaking, we're going to be arriving at sets of samples for this distribution, which we can then use in all sorts of ways noted in the previous slide. That is these ways down here. So it's really this approach is going to give us an ability to sample from the posterior distribution, which is going to be very, very valuable for allowing us to derive these sort of statistics for identifying the relative desirability of different interventions, the level of difference between different intervention gains, for example, arriving at point estimates or distributions for model output going forward. Now, I had mentioned the MC here is the second MC is from in MCMC is from Monte Carlo. The first MC is Markov chain, so it's Markov chain Monte Carlo techniques, and this term is used because it's actually used. An implicit Markov chain is used to generate the samples from the parameter space. So within this distribution, we've already started using some of the notation. Theta is going to denote parameter values, values in parameter space. These are going to be parameter vectors. As I noted, these parameter values could be parameters within the simulation model on the one hand, or indeed parameters within a probabilistic model that's going to express the likelihood that a given set of simulation model output could explain the observed data. And to denote the observed data, the empirical data, maybe it's time series, maybe it's particular data points, and that we to which we want to have the simulation model match. This would be the sort of data that we're traditionally trying to match within a calibration experiment. We're going to denote that data y. An important point here is that both theta and y are in general vectors, and they can include, in general, many components. So I'd like to give a glimpse of the high-level operation associated with using Markov chain Monte Carlo techniques for parameter estimation using simulation models. I'm doing this because this may be all that some of the people listening to this may need. I'm also doing it because it's useful to keep in mind as a structure for the remainder of this presentation. Perhaps some of you want to refer back to this. So up front, when we're preparing a Markov chain Monte Carlo experiment for use with a simulation model, there's a set of tasks we need to undertake up front. to fully specify the problem. One of the first tasks is to assign prior distributions over parameters, for example, and over models. We can encode which model we want to use, in fact, with a categorical parameter. These prior distributions for parameters could be specified in a parametric fashion, for example, using analytic distributions, say normal distributions, or log normal, or gamma, Gumbel, etc. In other cases, we may wish to use non-parametric distributions. So we want to assign prior distributions. Those will capture our best guesses as to where parameter values might lie before we actually start rigorously comparing the model output to observed data. In some cases, we may assume a uniform distribution, or some other non-informative distribution. Secondly, and this is arguably the most novel and most important component of the whole thing, we need to formulate likelihood formulae to indicate the relative likelihood of seeing particular values of empirical data in light of values of parameters and this is the key component when we come to simulation, and simulation model output. So suppose that we have some values of parameters that have yielded corresponding output from the simulation model. We need to specify likelihood functions, formulae that will determine for that given parameter values and corresponding simulation model output, what's the relative likelihood that could yield the some observed empirical data. So, for example, perhaps we have observed empirical data on the number of emergency room admissions for each successive week for H1N1, and we wish to we'll arrive at, and we have an underlying simulation model that simulates the number of incident cases of H1N1 within the population. We might be able to run that simulation model for a particular set of parameters, and it would give us over time for each successive week the number of incident cases for that week. And we would then have a likelihood formula, which would be a probabilistic model that would specify the likelihood that given some particular output from the model, some particular set of cases over time that exists in eventuality, what's the likelihood we actually get the observed number of cases that were historically observed over time. And that probabilistic model that would give us this likelihood function would typically involve some parameters of its own. Perhaps the likelihood a given person who develops flu symptoms will in fact present for care at the emergency room rather than convalescing at home. Now, given these components, conceptually, and this is not something we have to do explicitly, we conceptually apply Bayes' rule to get a rule for the likelihood of a given parameter in terms of data and priors. So given the likelihood, given the prior, by multiplying them, we're going to get a relative likelihood that we're going to get an estimate for the posterior, the relative value of the posterior for a given set of theta, implicit simulation model output resulting from that, and how likely that is to explain the data. So Bayes' rule is conceptually applied to arrive at the posterior then. We'll see that's a very simple step. It simply involves multiplying those first two elements, the prior and the likelihood. Now, then during model operation, a Markov chain is used to generate samples of parameters successively from this posterior. So we're going to be generating samples in a fashion that that is essentially simulating the or is drawing from the underlying parameter distribution in a way that's proportional to the underlying posterior distribution. And for each such generated parameter sample, for example, we could sample output measures of interest, accumulate statistics, or we may wish to just accumulate the samples over time, perhaps a certain number of them, perhaps it's 200,000, and later we'll go back and use those samples to run the model to get, for example, outputs of interest, etc. So one question that a lot of trainees and students bring to bear when thinking about these techniques is confusion about the Markov chain that is associated with this. There's often an assumption that because this is Markov chain Monte Carlo technique, that Markov chain must be reified in a very noticeable way. Maybe it has to be explicitly visualized and constructed and laid out. Well, it turns out that the Markov chain that's involved in this process is indeed extremely important, but it's really not typically reified. It's left implicit within the code. This is going to be a simple means of generating samples from distributions, and we're going to use it in a very flexible way, as an extremely flexible means of drawing values from a posterior distribution. Now, this may seem like a puzzling thing. Why do we need a Markov chain technique to do this? Well, it's worth reflecting on the fact that if we have a distribution which is known, if we have a distribution, for example, which is associated with some analytic expression, often we can arrive at an analytic expression for the cumulative distribution function. And if we want to, that will allow us to draw a random number from that original distribution. Specifically, if we know the CDF, we can draw a random number from a uniform distribution. And then we can essentially invert the CDF. We can return parameter values that give a cumulative probability that is equal to the value x we drew from the uniform distribution. This is a well-known technique for drawing samples from distributions. We know really well, and it's very easy to draw a random number from a uniform distribution. And given that, if we have an analytic specification of a given distribution, of the CDF, the cumulative distribution function of a given distribution, we can use this trick to sample from that cumulative from the underlying distribution. We can use the CDF to draw values from the underlying distribution. The problem is that while this technique is very powerful, it only generalizes somewhat awkwardly to a higher number of dimensions, but more fundamentally, it exhibits problems when we don't know the CDF up front. If we can't arrive at a specification, a full specification of the CDF, of the cumulative distribution function, we can't proceed in this manner. We can't simply invert the CDF value, having drawn this number from the uniform distribution. If we can't specify the CDF up front, we can't undertake this traditional way, and it becomes very awkward anyway in large numbers of dimensions. So we need another way besides this traditional way, this way illustrated up top, to draw values from arbitrary distributions. This trick that we use with the CDF, where it's great for simple distributions where the cumulative distribution function, the CDF that is known exactly, but it does not work well if we can't formulate that distribution explicitly, the cumulative distribution function. So a Markov chain approach lets us generate samples from the parameters from the posterior without knowing uh, the shape of that posterior or its corresponding CDF in advance. Okay, we'll talk a little bit more about that later. Now, a critical conceptual underlying piece of this work is its reliance on what's known as Bayes' rule. Now, those who are viewing this will likely be familiar with the fact that Bayes' rule relates the likelihood of A given B to the likelihood of B given A. So, given some statement via what's called the likelihood function here, the likelihood function that a given set of empirical data could result from a particular values of parameters, and given some initial posterior, some initial guesses as to the relative likelihood of different parameter values, we can arrive at a distribution for the likelihood a given set of parameter value obtains given the observed empirical data. So Bayes' rule allows us essentially to flip around a situation where we know a posterior or a prior and where we know a likelihood that y could be explained given a set of parameter values. Lets us flip that around to get an estimate to give us a sense as to the probability of a given set of parameters obtaining in light of known y. So if we have a way of saying, for example, for these sets of parameter values with my model, these sorts of number of incident cases at time 20 has this level of occurrence, that it's very unlikely to be below 10 or above 20, and it's much more likely to lie between those. If we have some way of specifying the relative likelihood of observed empirical data given parameter values, then we can leverage that to arrive at a distribution for the relative likelihood of that certain parameter values obtain. We're essentially using our knowledge of what empirical data is likely to occur for a particular set of particular parameter values to constrain our understanding what the possible values of theta are. So here we're going to introduce these terms. P of theta given y is the posterior probability of theta. We want this. In light of the empirical data y, we want to have some understanding of the relative likelihoods of different parameter vectors obtaining. That is the relative likelihood that we have these sets of parameter values or these other sets or these other sets. Maybe it highlights first two sets are modestly likely, the third set is extremely unlikely. This is what we're trying to arrive at, P of theta given y. The likelihood of different parameter values given the empirical data. P of y given theta is what we bring to the table in terms of our likelihood rules. I mentioned it here, this likelihood formulae. We have likelihood formulae that indicate the relative likelihood of seeing particular values of empirical data, such as particular counts of emergence room intakes for H1N1, in light of particular values for theta, for the parameters in the corresponding model output. So P of y given theta gives us something we bring to the table. Hey, how likely is it, for example, you saw this many people in week 2, you would have seen this many people in week 2 if you had had these parameter values. Now P of theta is a prior. That's what we specify ahead of time given our sort of relative likelihood of different values obtaining. Sometimes we just impose an informative prior, a prior that, for example, is uniform over some bounded theta space. In other cases, may come with strong assumptions based on rough knowledge confided by experts. P of y here, which is in the denominator, is notable. The likelihood of sort of different empirical data is notable because it's just a constant. It doesn't vary at all with theta. So when we're assessing the relative likelihoods of different thetas, we don't have to worry that this will depend at all in terms of theta. It's just a normalized, you could think of it as kind of a normalizing constant, some coefficient times this thing here. So this is really where the action's going to be. We really don't have to worry about this. In fact, we'll just ignore it and just talk about the relative likelihood of theta given y. There's some coefficient in front of it, but as long as we're drawing samples from theta in a way that's proportional to their relative likelihood, we're in fine shape. In short, y does not depend on theta. On theta. So to compute the relative value of put it another way, to compute the relative value of two parameter vectors, theta 1 and theta 2, all we have to do is compute the value of this sub-expression here. That is this one versus that one. P of y is multiplied, 1 over P of y is multiplied by both, and it's a normalizing constant in front of both. We don't have to, or it's a constant in front of both. We don't have to worry about its particular value. I should note that I'm using this term parameter vector. What I mean by that is an assignment of a particular value for each successive parameter. So maybe the contact rate is 10 people per day, and maybe the hand hygiene compliance rate is 50%, and maybe the some mean time to recovery is 3.2. Recovery from infectiousness, duration of infectiousness is 3.2 days. That would be a particular parameter vector, particular value vector within the space associated with theta, a particular theta, as it were. Maybe it's theta 1. Another particular theta might be associated with an assumption of 20 people per day contact rate, also 50% hand washing compliance, and also 3.2 day average days of infectiousness. Those are parameter vectors. Okay, so let's talk about the use of this Markov chain to sample from this posterior distribution. Essentially, what we're going to do, and this is an approach associated with Metropolis Hastings type Markov chain of Monte Carlo approaches, is we're going to draw a candidate value from theta, okay, and in a particular simple case, a random walk Metropolis Hastings will be seeing. This is just generated from random perturbations around the last generated sample. So we're going to draw a candidate value, and then we're going to assess the relative likelihood of this candidate value of theta. Okay, and should be careful here. We're going to assess the relative posterior for this candidate value of theta. I was speaking informally here, and just to reduce confusion, I'm going to update these slides accordingly. So we're going to assess the relative posterior for this candidate value. So how are we going to do this? Well, generally speaking, P of y given theta typically is going to assess that in order to arrive at an understanding of how likely, for example, it is that you see 5 people have presented to the emergency room in week 2 of this pandemic with H1N1 for a particular set of parameter values, for for this for 10 people per day contact, for 50% hand washing compliance, and 3.2 days average infectiousness, to assess the relative likelihood that that's going to yield 5 people being observed within week 2 of the H1N1 pandemic in your city, you're going to need to typically need to arrive at output from the simulation model. That is, you're going to need to run the simulation model, because looking at those parameter values in and of themselves is not going to tell you the implications for how many people per day are, how many incident cases are there within that week, for example. It's not going to tell you the key information you're going to need to assess the relative likelihood of the empirical data Y. To arrive at an understanding of that likelihood, we're going to need to run the simulation model. That may give us the number of incident cases within that week that are implied by those parameter values. And given some representation of the underlying incidence for week 2, as specified by running the simulation model, on the particular parameter values, now we could formulate the relative likelihood. So given that there's, say, the simulation model tells us that there's 20 people, 20 incident cases to be expected in week 2, we can then assess the relative likelihood that we only see 5 presenting at our hospital. And again, that might involve some additional probabilistic model calculations, such as drawing from a binomial distribution where each person has a certain chance of presenting given some underlying illness. So in the first step here, we're going to run the simulation model. In the second step, we compute the relative posterior. We're going to take this assessment, that we can compute the likelihood of the observed data in light of theta in the associated simulation model output implied by theta. So that will give us P of y given theta, and then we'll multiply it times P of theta. Now, finally, this is all for a candidate sample, a candidate parameter vector. And we're going to accept or reject this candidate. That is, we'll either emit it or just throw it out based on the ratio between the relative likelihood, the relative posterior. That is based on the relative the ratio between the relative posterior at theta and the value of that relative posterior to the last generated sample. Will either accept this new one or reject it. If we accept it, we release it as our new sample. It's a sample from the distribution. If we reject it, we emit the existing value. We don't change position. We reject this candidate, emit the previous value we emitted, and we go on to the next candidate. So very importantly here, it's important to realize that the greater the value of the relative posterior at this candidate theta, the greater the likelihood we'll accept it and emit that. So if it's a very, very likely point we've arrived at, if the candidate is extremely likely, has an extreme high relative value at the posterior, we're much more likely to accept it. So those points will tend to be sampled more, that is, emitted more. By contrast, if we're in regions of space where things are very unlikely to occur, then this ratio will typically be smaller, will more typically reject, and so we'll tend to sample those things less. So this algorithm provides sort of its internal throttling to such that it will emit more frequently things that are more likely to occur, and less frequently things that are less likely to occur. Now, in order to apply this algorithm appropriately, we're going to need to run through some burn-in time before using the results. That is, in order to arrive at confidence that the samples will be representative of the underlying posterior we're trying to approximate, we need to run it enough times that it sort of forgets about the vagaries of where it started, and sort of gets into the groove, as it were, in terms of mixing well within the parameter space. So we don't want it to depend on accidents of where we happen to start in the space. We want it to kind of get to a point where it's sort of forgotten where it started, and it's well mixed. So a common way of implementing this that I've already been sort of using for illustration is using a very simple approach called random walk Metropolis Hastings with symmetric perturbation. The idea here is if we find a high relative likelihood point than the current one, we go there automatically. So this is in the acceptance. If it's higher than our current relative likelihood, we automatically go there and emit that sample. If we find a lower likelihood point than the current one, we only use it as a new sample with a certain probability as given by the ratio of relative likelihoods involved. And that P of y, you'll notice, drops out. If we're dealing with the ratio of this guy here for theta 1 and this guy here for theta 2, P of y totally drops out. It doesn't depend on that at all. So if the candidate sample involves a lower likelihood point than the current point that was associated with the last emitted value, then we'll only go to that with a certain probability. Otherwise, we stay with this higher likelihood point. So, in short, these high likelihood points get relatively sampled more. These low likelihood points are relatively sampled less. Okay. And that algorithm could be expressed here. So initially we pick a value, we can draw it from some crude distribution. It tends to be forgotten within the burn-in period. And until some convergence criteria is satisfied, we pick a random value for our perturbation from our last accepted point. We create a candidate value. So to use kind of consistent terminology, I think I'll say a candidate value, and I'll adjust that. Candidate value at this theta tilde. And depending on the ratio at the last accepted point and this point, we either accept or reject. And it's automatically accepted if the new value is of higher likelihood. Okay, and otherwise it's rejected, and then we'll emit the new point. The new point may just be the old point. No, we stayed at the old point. We'll emit it again. That's the sort of aspect of sampling more from points that are higher likelihood. Otherwise, we go to the new point and we'll emit that one. Then we go on to a next iteration. So why does MCMC work? Well, there's a whole theoretical edifice built around this that I don't have time to explain here. But fundamentally, there's only one stationary distribution for the Markov chain. The actual posterior is a stationary distribution, and therefore it must be the unique one. So if we run this algorithm far enough, we'll get a distribution of values very close to a posterior. Now, I thought I had some comment on why this is a Markov chain. Well, where's the Markov chain? Well, at any given point where we have a particular value associated with theta sub I, associated with our current point, and we have a certain chance of transitioning to another value of theta. We have many possible thetas we could get to from this state. We could go to other states with certain likelihoods, with certain probabilities from that state, based on this relative likelihood of transitioning. That is based on this ratio here. So you could think of that whole process as involving transitions along a Markov chain, where each state of the Markov chain is associated with being at a certain point in parameter space. The Markov chain is implicit within this algorithm. This algorithm is capturing the behavior of the Markov chain, even though it's not reifying it as a software object or anything like that. Okay, where does the simulation model fit into this whole approach? After all, we've been talking about these Markov chains and these sort of likelihood rules and so on, and priors. Where does the simulation model fit in? Well, typically it's, in case this hasn't really struck you yet, it's the critical mediator between, on the one hand, the parameters, and on the other, the observed data. So typically, in the sort of situations we'll be dealing with, we're going to be reasoning about consistency between the model's emergent properties on the one hand and empirical data on the other. And typically, in order to assess the likelihood a given set of empirical data would have resulted from a particular value of the parameters, a particular value of theta, we're going to need to reason about the emergent behavior of the model based on theta. And almost by definition, that emergent behavior is going to require us to simulate the simulation model. In many cases, it may be a nonlinear simulation model, perhaps, for example, associated with infection transmission of norms and ideas, etc. And we're not going to be able to arrive at its emergent behavior without plugging in a value of theta and running it, and then observing the consistency in a probabilistic sense, assessing the relative likelihood that that model output, together perhaps with considerations of the actual values of parameters, would yield the observed empirical data. So the model, in short, helps us project behavioral consequences of parameter assumptions in light of dynamic hypotheses captured by those models. And typically, the estimated likelihood that this output data will be observed, that is, the value of this, relative likelihood that the output data will be observed given a particular value of parameters, is typically conditional on simulation model outputs rather than directly in the parameter data. We typically need the emergent outputs from the model given assumption of parameter values theta to assess the likelihood that the observed data would occur for these parameter values. So in short, and forgive me if I'm beating a dead horse here, in order to assess this value, p of y given theta, we're going to need to run the simulation model with parameter values theta, arrive at simulation model output before we can assess this likelihood. Because we're going to need in our probabilistic model to refer to things that are output by the simulation model. I should note, and I'm not going to comment on it here, the prospects for using this with stochastic simulation models, which are an important component of the sorts of models we build, and are of considerable interest when you're thinking about generalizing predictor-corrector models, such as are used with the Kalman filter, generalizing them for more diverse error models, for example. I'm not going to talk about that here. For the moment, I'm assuming a deterministic simulation model. One thing that's notable here is that if we wish to secure insight into posterior distributions over different simulation models, the identity of the appropriate simulation model can be just treated as another parameter in theta, a categorical parameter. So we can have a theta, for example, that selects one of several different competing models. That's just another element of theta, just another dimension in theta space, although a discrete one. Now, as you probably have appreciated, the likelihood formulas are the key nexus here. The likelihood statements P of y given theta must be specified by the Markov chain Monte Carlo model creator to assess the likelihood of seeing particular empirical data values in light of parameter values. These are the key factor in judging the relative likelihood of different parameter values for a model, and they have to be thought through typically very carefully. Commonly, they will involve a probabilistic model that is used to calculate that likelihood. That is, draws from probability distributions to assess the likelihood. Excuse me, not draws from probability distributions, but assessing the value of probability distributions at particular points within their support, that is, within their domain. So suppose the simulation model, for example, has a stock of diagnosed individuals with TB at a given time t. We'll denote that as d sub t. We might express the relative likelihood that a given count of diagnosed individuals, lowercase d sub t, was reported at time t in empirical data. So given some value from our simulation model at time t, we might want to assess the relative likelihood that we have that will be consistent with the relative likelihood to assess the consistency of this value from the simulation model with this empirical data. That is to assess the relative likelihood that a given empirical count of individuals, d sub t, for that same week would be reported. And to do so, we might assume, for example, we use a probabilistic model. We might assume that for each diagnosed person, there's a probability delta of being reported, and indicate that the likelihood of this many empirical people being reported, given this many true people being diagnosed in the population, is proportional to binomial d sub t of theta. So just to be clear here, this should be reported. Apologies, but I figure it's better to have it fixed. What's the likelihood we actually would observe this empirical data if we actually had this many diagnosed individuals in the population? Well, to figure that out, we'd assess the likelihood given a binomial distribution that we see this many cases for this many as the result of this many tries, each associated with this probability of being reported. We're assuming that they're independent there. The likelihood of each one being reported is independent, theta. So this is a probabilistic model. To arrive at this likelihood here, theta, we would first run the simulation model and get this dt at time t. And then we would go and assess the likelihood that d sub t results from a binomial distribution with this many tries and this many tries in this likelihood of drawing for each try. Okay, so here we are assessing the likelihood that certain observed data occurred given underlying output from the simulation model and some probabilistic model parameter delta. This data delta might be part of our theta space, for example. That might be something we wish to include in our model. Now, I think what I'll do is, just to have this be clearer, I'm going to write this in here. So this would now be, we're assessing the value of the binomial distribution with these parameters. I'll put a semicolon in here, with these parameters at this value. Okay, so we talked about this process. I hope it's fairly clear. We have this whole algorithm that's going on, and typically to arrive at this estimate of this posterior, the key component of it is this likelihood, and we use that to accept or reject successive values of theta. So to be clear here, we're arriving at the value of the posterior by multiplying these sort of things, the prior on the one hand via this likelihood. This likelihood is typically, to compute it, we typically need to run the simulation model to arrive at some intermediate values like d sub t. We then apply a probabilistic model that gives the likelihood of observing the empirical data in light of perhaps parameters within the probabilistic model and the data from the simulation, as well as any required values from the parameter vector, otherwise in the parameter vector. So this process, one thing to recognize is that running the simulation model often takes a very, very large amount of computational effort. Here we are, this often to do this, we're going to be running the simulation model regardless of whether we accept or reject a candidate sample. We're going to be running it. We have to run it to arrive at an estimate that's relative posterior. This knowledge of the posterior up to a constant that we arrive at through this product here. So to calculate these quantities throughout this whole iteration, we're going to be running the simulation model for each iteration, regardless of whether we accept or reject. And often we may run it hundreds of thousands of times to arrive at that those sufficient set of samples from the posterior. We also typically run a burn-in period so that it's essentially memoryless with respect to the initial point in the chain that we choose. That is, so that it's kind of forgotten this theta sub 0. We're going to run it through a burn-in period that could itself be hundreds of thousands of runs or tens of thousands of runs. The good thing is that much of this work can be done in parallel. Often, for example, we make use of different walkers, so that we'll have several walks of this sort going on in parallel, for example, on different cores or in different machines, in essence, taking advantage of the embarrassing parallelism associated with this. There's dependencies, to be sure, within a given iteration, a given use of this walker, but we could have several walkers operating at different areas of the space in time. Let's talk about some practical concerns beyond the raw computational effort. First issue is burn-in time. Typically, we do need to run it for long enough. It starts generating values approximately distributed as posteriors. And there are ways of doing this. If you look at the book Bayesian Data Analysis by Gelman and et al., you'll find discussion of, for example, ways to assess convergence of the algorithm. Burn-in time is one of the choices we have associated with how long we're going to run the algorithm. We want to tune the algorithm parameters, such as the perturbation size used to the random walk. In other words, just how far this delta theta brings us. How far do we move in delta theta to yield an acceptance rate that's acceptable? We don't want to have 1% only of candidate samples accepted. Now, different authors will make different suggestions for this, and this is one set of recommendations you'll see in the Gelman book. Others will argue, for example, for higher acceptance rates. This is not a correctness issue, this is an efficiency issue. You certainly want it to be high enough to explore, so you don't just remain in the same space. You're not stuck in a space. It makes it extremely unlikely you move anywhere, because you won't be getting samples that are representative for the entire space. You want well mixed, so you're moving around parameter space. But you don't want it to be so high that just going around in the local area of the optimum without significantly improving the estimate, where it's always just sort of accepting things nearby. So in other words, you want a large enough perturbation, you get out of your comfort zone sometimes. Other practical concerns. Well, turns out that the efficiency algorithm can be greatly adversely impacted by covariance in the posterior distribution associated with different parameters. If two parameters, for example, exhibit high covariance in the posterior distribution, essentially it may be walking a ridge in 2D space, and that's going to take a lot of rejections and so on to stick on that ridge. There can be a lot of jumps that go outside of that nice zone and need to be brought back onto that ridge. You're essentially exploring a sort of 1D structure in 2D space when the intrinsic dimensionality is close to 1, even though it's embedded in 2D nominal space. If you have this high covariance between parameters in the posterior space, it really can lower the efficiency of the algorithm. And the suggestion here is you might want to decorrelate or eliminate much of the covariance by essentially doing a regression on some initial outputs from the model, and then you could do walking in a residual space. Many algorithms for doing Markov chain Monte Carlo, implementing Markov chain Monte Carlo algorithms that you could ride atop, such as the wonderful R libraries, such as the Metrop1R in MCMC pack. They either presuppose or make it much easier if you're operating in unbounded space. And so often what this leads is if you have a parameter you only want to vary, say, beta within a infectious disease simulation model, you want it to vary between 0 and 1. You're going to want to transform it so that it is so that it's associated with an unbounded space. So, for example, you could take a logistics transform of it. Or if you have a parameter that can only be 0 and higher, you may want to take a log transform of it, so it can go from minus infinity to plus infinity. That will allow the algorithms, which are sort of dumb with respect to boundaries, to operate. Another option is to do resampling, but this may involve custom coding on your part to implement the underlying algorithm. Another issue is, particularly if you're seeking to use the successive samples in some successive way, you may really put a premium on reducing correlation between successive samples. In any case, if you have high autocorrelation between successive outputs from the simulation model, you're going to need to sample further. Each successive one isn't going to be telling you a lot independently about, it's not going to be sampling from the space in an independent fashion. So the effective sample size may be much, much lower than the nominal sample size. MCMC pack has some nice tools for assessing, for example, effective sample size, and it also provides a way of so-called thinning the results, which is very common, only accepting 1 out of every n samples. This is not required in all cases. Generally, just can sample a lot more, Just be aware your effective sample size may be much lower, and you may be really fooling yourself if you're treating them as independent samples. To assess convergence of the overall algorithm, this is not specifically about burn-in time, but converges more generally. The book by Gelman, Bayesian data analysis, has some nice discussion about using between Walker and within Walker variance to assess how much will be gained by further sampling. Essentially, if within Walker statistics are similar to those between Walkers, maybe a sign that you've done a pretty good job exploring the space for each Walker, and there's not much additional need to run further within a given Walker. Now, it turns out we've only touched on the issue of MCMC algorithms and just in a very crude way. There's actually many variants of MCMC algorithms. These differ in the range of applicability and simplicity and sophistication. For example, some of the more advanced models, such as reverse jump MCMC, choose between models of different numbers of dimensions, say different numbers of parameters that are applicable. Some allow for asymmetric random perturbations versus assuming symmetric perturbations. In other cases, you can have great extra efficiency if you can do things like Gibbs sampling, where you've successively conditional formulation of a model. You sort of build it up as using successive conditionals in a way that doesn't force you to do rejection, that sort of guarantees you arrive at an acceptable sample. I talked about the implicit Markov chain. I don't think I'll go through that more, but the idea is that each state is associated with a particular point in space, and you have these transitions between different different states associated with the likelihood of accepting the relative posterior different points. And that's not a reified object, the Markov chain generally. There's also, you should be aware, a set of Monte Carlo methods that span different sorts of needs when it comes to incorporating new data. So what we've been talking about here, MCMC, are batch or offline Monte Carlo algorithms. So they process all data at once. We have all data of Y at once to yield a posterior. If new data Y arrives to be incorporated into Y, we can run the algorithm entirely again. Now, in some cases, that the computational cost may be prohibitive to do that. We may need to quickly incorporate the new data into our estimates for the posterior. Now, it turns out that, or otherwise our distributions that we're interested in. It turns out there's a class of sequential Monte Carlo methods, most notably particle filtering, that are more restrictive in terms of the distributions they arrive at. They're similar in a way to extended Kalman filtering in the sense that they allow you to incorporate new data and it's defined recursively. You don't have to go back and recalculate the entire algorithm from scratch. You can use the results from the data you had earlier and update those results in light of the new data that's available. However, they're far, far less restrictive in terms of their distributional assumptions than as Kalman filtering. The sequential Monte Carlo techniques can be much more efficient than the sort of batch technique we just looked at, although they are somewhat more restrictive. And it turns out there's a simpler technique called rejection sampling. When you have knowledge that can bound the posterior distribution, it may be effective. So I've just given you a brief overview of Bayesian estimation of simulation modeling parameters via Markov chain Monte Carlo techniques. I apologize for not being able to go in greater detail. This is a very, very rich, powerful, and flexible technique, and one that's challenging to present in a really confined time. I've had to really go light on a lot of details and gloss over some things. But I hope that you will find it useful in your planning for incorporating rich statistical techniques together with your dynamic models. Thank you very much, and have a good day.